So in this video, we're just going to go through another example. I might recommend pausing the video as much as you can to try to work the problem yourself before you see the answers, because sometimes that can be very helpful to see if you're on the right track by actually trying it on your own first. One thing to note here is if you've printed the handout, all of the output that you're going to need is here on the very last page of the handout. I will also be showing you how to get that in StatCrunch again. Alright, so figuring out the problem here, so we're trying to see if age is a good predictor of number of doctor's visits in a year. So looking at our variables, we have age and we have number of doctor's visits. Both of those are quantitative, so that's how I would know I'm inside this set of notes. We took a random sample of children between age 0 and 16, and the number of doctor's visits they had in a year was recorded. Again, all your output is on the last page. So first, which one is the response variable and which one is the explanatory variable? Well, the response variable here is going to be our number of doctor's visits, because that's what I really want to know. And then the explanatory variable will be age, because we think that can predict the number of doctor's visits. Next, we're going to interpret that scatter plot. So again, for you, it's on page 13. But I'm also going to create the graph here with our doctor's data set. So graph scatter plot. We just said age was our explanatory variable and visits was our response variable. So here is what my scatter plot looks like. Kind of going through my questions, it does look like a straight pattern. It appears to have a negative slope, meaning the older children get, the less doctor's visits they tend to have. Strength-wise, maybe somewhat strong, and I don't really see anything unusual. So I'm going to take that time to write that interpretation out. So then here's that interpretation of mine. Our relationship between age and doctor's visits is linear. The negative slope, meaning children tend to have less doctor's visits as they get older. It's a somewhat strong relationship with nothing unusual. Next, we're going to write out the equation and interpret the slope and intercept. So looking first at my output here, and I'll regenerate it here so you all remember how. So stat, regression, simple linear, putting in my x and y. So the main things I need right now are my intercept and slope estimates. So I'm going to use that to write out my equation. So my slope is negative 0.3137. And my my intercept is 5.7081. So then my equation will just look like that. So then we're going to interpret the slope always and intercept if appropriate. So let's go through the slope first. That's our negative 0.3137. Alright, so remember what slope is measuring. So as x gets bigger by 1, so that means our child's going to get a year older. So for each year older a child becomes, then what's going to happen to doctor's visits? Well, it's going to go down, since my slope is negative, by about 0.3137. So for each year older a child gets, we expect doctor's visits to go down by our 0.3137. Okay, now let's talk that intercept. And if you remember, there's 3 questions we're going to go through. So the first one is, can x equal 0? Well, X is our age of a child. So the question is, can a child be 0 years old? Well, it says up here we even sampled people who were between 0 and 16 years old. So X can be 0, age can be 0, because you're technically 0 years old when you were born. So that's what that age equal to 0 means. So that's possible. Can Y be approximately this number we got? And we're talking about then doctor visits. So is it possible to have between like 5 and 6 doctor's visits in a year? Yep. And then that last one is if we have any data near X equals 0. So we need our scatter plot there. So let's bring up this one. So let's think, okay, so this is about where 0 is. So 0, 5, 10, 15. So we do have values close to 0 in our data set. So since I have yes for all of them, I can actually interpret this. So I can say, so a child who is just born can expect to have basically between 5 and 6 doctor's visits. So that's what that intercept would be telling us. Right, so I would say that slope is one of the things that we struggle with. So notice in our first example we did, you had a positive slope, and this one then has a negative slope. At this point, I really do recommend pausing the video and trying the next few on your own, and then coming back to see if you agree. So looking at to see if there is a relationship, we're going through all steps here. So our null hypothesis is that there is not this linear relationship between doctor's visits and age. And the alternative is that there is this linear relationship between doctor's visits and age. Remember, this first one is the response variable, and the second one is the explanatory variable. Now we have the same second step that we've always had. So we're just going to reject the null and believe the alternative if our p-value is less than alpha. And we're told to use a 5% significance level. So then checking our conditions, remember we're not actually going to formally check these. They're just going to be things we assume, but we list them anyway so that we realize what we've assumed. So we need the idea of normality at each value of x. We need this same constant population standard deviation throughout. And our y's would need to be independent of each other here, where y is again is our number of doctor's visits. So the idea of independent y's would mean we believe that one child's number of doctor's visits has no impact on another child's number of doctor's visits. So again, we're going to assume those. All right, next we're calculating our test statistic. So we need our value of slope, which was our negative 0.3137. Again, this minus 0 is coming from the idea of no relationship, saying that we'd have a slope of 0 to begin with. Then that 0.0253 is coming from our StatCrunch output. It is our standard error that's associated with slope. And then notice after I did that math, I got that negative 12.39. And our next step, we're going to be pulling off this p-value, keeping in mind that we're pulling off the same one that's attached to slope. All right, so looking at our p-value calculation, again, I always draw the picture just to try to understand what's going on. So remember, t and z are a lot alike, and so we kind of expect most of our values to be between 3 standard deviations below and above. And notice that we are 12 standard deviations below. That's why this p-value that you're getting your output is just so tiny. It's so far away, so it's very, very unlikely to happen. Since our p-value is less than that 0.05, I am going to reject the null and believe the alternative here. All right, so this time for our interpretation, alpha is 0.05. Since we rejected, there are statistically significant evidence that the number of doctor's visits is, since we're believing the alternative, linearly related to age. Technically, again, we're kind of adding. We know it's a negative impact because our slope was negative and because our t was negative. So these signs will always match here. All right, moving on to the next problem, we're talking about strength here. So it's going to be looking at the r and r squared, which are right here for you. And then you've just got to worry about interpreting them. So then doing our interpretations, r here is negative, and since it's pretty close to -1, I'm calling it pretty strong. For r squared, it's a more exact interpretation, so we change that 0.729 to a percentage by multiplying by 100%, so 72.9% of our variation in y, which is number of doctor's visits, can be explained by our x, which is age. If you look ahead, F and G are very similar to each other, except for the age of the child that we're looking at. So here you're looking at interval, so this goes back to confidence versus prediction interval. So first, let me just kind of remind you of how I got the output that you're going to see for that. So when I actually run to get this analysis that we were already looking at, I just need to add an extra feature. So I'm still keeping this the same, but then down here for that prediction of y, I put in the age of 3, and I use a comma to separate them, and put the age of 20 to get this additional output that you see where I just rounded some of the numbers that you see. Alright, so let's talk to the first part of the question. If appropriate, find the predicted number of doctor's visits for a 3-year-old. So really to find the idea if it's appropriate or not, can you be a 3-year-old child? Does that make sense? It does. If I go back and look at my data set, I had children near the age of 3, so that makes sense to look at. So to find the predicted number, I'm just going to plug 3 back into our equation that we had here in part C, right? So now my x is age, my age is 3, so I can just plug that number in. Then it tells me to interpret the appropriate interval. Now for appropriate interval, I've got to choose between the confidence interval or prediction interval. So the question is, am I looking at a group of 3-year-olds or a single 3-year-old? Well, it says a 3-year-old, that's an individual, telling me then that the prediction interval is going to be what I want to look at. So then looking at my output, I'm looking at 2.87 to 6.66. So I'm going to interpret that, keeping in mind that we're looking at an individual child. So keep in mind, again, since it's an individual child, they can't have a decimal number of doctor's visits. So when I did my interpretation, I said I can predict with 95% confidence that a 3-year-old will have between 3 and 7 doctor's visits. Remember, with prediction intervals, there's never anything about that average showing up in here, because that's for a confidence interval when we're talking about the mean. Now go ahead and try G. Well, here is the answer I hope you came to, is that it's actually not appropriate. Now, why is it not appropriate? Well, we had children in our sample between the ages of 0 and 16. And even once you reach the age of 20, would you really consider yourself a child anymore? So I would say it's not appropriate because 20-year-olds are not part of my population. So I only want to use this model when it's appropriate. I can plug in really any number I want. StatCrunch will let me plug in any number I want, but I've got to make sure it's a number I should be plugging in. All right, you have one last video just looking at some kind of cautions when we do the relationship between two quantitative variables.